So, good afternoon once again. My name is Claudia Brito, and I'll be your moderator for this session today. And I want to welcome everyone to today's Epicure webinar, Python on GPUs, and how hard can it that be? And we are thrilled to have you join us to explore the main approaches about Numba. And to introduce our speaker, and Geert Jan Bex from has been working for the Vlaams Supercomputing Centrum since 2009. And besides user support, his focus is mainly on training. And over the years, he has developed or provides training sessions on scientific computing, parallel programming, and GPU programming, as well as machine learning. And I'd like to inform all of you that you can add, and you should add, interact during the presentation. So use the chat. And you can share your questions during the presentations. There are no discussion moments, but at the end of the webinar, we'll provide some minutes to discuss all the questions and interact directly with you. I will be monitoring the chat activity regularly, so to ensure all the questions that will be answered in the end and at the right time. And so we now move to the presentation. Please keep in mind to keep your microphone muted, and Geert, I think the screen is yours now. Thank you.
Okay, thank you for the introduction. I hope you can hear me. Okay. So, Python on GPUs or using GPUs, how hard can that be? Well, the answer, of course, as usual, when you ask me something about HPC in general, then the answer is, well, it depends. And that will also be a little bit the thread throughout this presentation, the thread throughout this webinar. So, as usual, simple things are relatively straightforward, but yeah, to get something more interesting and better performance, it's not always that simple, and we'll explore a little bit how that works. I chose this particular presentation and Numba as a framework because it's pretty accessible. So using Numba, as you will see, is quite straightforward. Of course, it's not your only choice. In fact, there is a whole ecosystem of GPU libraries out there which you can use for scientific computing in general. So there are frameworks like PyCUDA, there is PyNumeric, there are, of course, all the frameworks that are in fact developed for machine learning, but that you can happily use to do scientific computing as well, such as, for instance, TensorFlow or PyTorch. So there are quite a lot of options. But at the end of the day, it doesn't really matter that much which you use. What is much more important is that you clearly understand the principles behind GPU programming and the potential pitfalls or opportunities for optimization. And that's a little bit what this webinar will try to show you how that works. Of course, when you finish this webinar, it's not as if you can immediately start your journey to port your code to GPUs using Python, but at least you will have some idea of how that could potentially work. Okay, so I'm not entirely suicidal, so I'm not going to do this really interactively, because of course then always things start to crash. So I'm not going to do that. This notebook has been prepared in advance, so I'm just going through it, not executing it step by step. Always too tricky to do that. So the notebook is available, as is the other training material from which this particular webinar has been a selection of. So that is in the public domain. You can feel free to check that out if you want to. Okay,
Będziemy
so
w GAI robić AI i w Plumie AI i trzeba się zastanowić.
Okay, I'm assuming that was not for me. All right, so as usual, Well, this is a Jupyter notebook. That's just because it makes it easy to visualize things. I'm doing this kind of, let's say, explorative programming in Jupyter Lab. And of course, that's a very good way of doing that. I should also note right now already that this training material, in fact, has been developed on my own machine. So basically, this is using a GPU that is not designed for doing scientific computing. It's quite capable of doing that, but it's not designed to do it. So one of the things that you will see regularly is a choice of data format, which might not be what you want, but that is just an artifact of the hardware I'm using. So no worries there. It's not as if that would be a limitation of the library I'm using. So I'm importing quite a bit of stuff. So basically the usual Python stuff, the math library, matplotlib, and so on. So the usual stuff. And of course, it gets considerably more interesting when we turn to the Numba imports. So basically, I'm importing a number of things that, as you will see, have to do with function declaration, and also a bit about random numbers, which I'll touch upon later. One of the things which is nice about Numba is that it works quite well with NumPy arrays, which you are most likely very familiar with. So basically, I import also that, and then, of course, random in order to get some random numbers at some point. Okay, so let's start with a very simple, very basic example. And the first thing I'm doing is implement that in pure Python. And if you look at the implementation, you see that this is in fact just computing the result of a Gaussian function on, in this case, either a number or on something that is list-like. And as you can see, it's really, really pure Python in the sense that I'm using the math module out of the standard Python library. So no NumPy, nothing special. Very simple, plain Python. Okay, I have this instance call here in order to more easily distinguish between executing this on a single number or on something that behaves like a list. That's why the is instance is there. It's, yeah, just a bit of cosmetics in a sense. Okay, of course I need data, so I construct that using NumPy. I'm using linspace, and I want a significant data set. So basically, I will have SX values, 1,000,000 points. So that is okay, not huge, but it's okay in order to do some timing experiments. And as you can see, as D type, I pick float 32. The reason, again, I do that is hardware limitations of the GPU, which is in my laptop or in my desktop in this case. So basically, that's just to ensure that the right data type is used. Okay, apart from that, I also define two constants, mu and sigma. And of course, I have to ensure that they are the right data type as well. So again, just numpy float 32 in order to make things consistent. Okay, I can execute that using magic, the magic time it, which, as you may know, it will execute the statement multiple times, and it will compute some statistics about it. So the average time it takes to execute, some measure of the deviation for that, and it will report on the number of runs and the number of loops in each run. And then you see that if I do that, the average time to execute this is 2.5 seconds. Okay, that seems a bit too much in the sense that you likely would expect that that would go much faster. Okay, there is an exponent function there, an exponential, so that takes a while. It's not the fastest operation you can imagine. Similar for the square root, but still, even then, this is, if you have some gut feeling for performance, this is slow. Okay, so what can we do? Well, we can use Numba in order to vectorize that code to, in fact, what is happening under the hood. It's going to take my Python function and it's going to translate that into a C function or a C++ function, depending on what happens under the hood. I think it's C++ if memory serves, and it's going to compile that automatically for me, and it's going to let me use the resulting function from Python. Okay, so as you can see, this is essentially the same Python function as before. The only difference is that this operates on a single number. So I left out this instance thing. Apart from that, it's identical. Okay, and in order to use Numba, in order to generate under the hood the C++ code, compile it, etc., the only thing I need to do is to add the vectorize decorator to my function. And what I need, or what I can do in order to help Numba generate efficient code, is specify the signature of my function. So basically, the data types it takes for its arguments. It has 3 arguments, x, mu, and sigma, and I'll declare specifically that all 3 of them are going to be float 32. So float 32, as you know, is a single precision, so that means 7 digits of precision. 7 significant digits. It also means that the maximum number is going to be 10 to the power 38, that the lowest number, the smallest number larger than 0 will be 10 to the power minus 38. Okay, so 3 floating point numbers as parameters to my function, and the function is going to return a float 32 as well. So this is the return type. These are the 3 types of each of my parameters separately. Okay, so that's all I need to do, and I can simply execute Gaussian. Okay, and when I do that on the same data, you actually see that now the execution time has dropped dramatically by a factor of around 500 for this run. Of course, your mileage may vary. It depends on the hardware. This has run on a rather powerful workstation slash laptop. So yeah, it will depend on what you have under the hood. Okay, so this ran on the CPU. And as you can see, without much effort, I got a huge speed up. Let's now do the same thing for GPU. So how much more complicated is that? Well, essentially, not very much. The only thing I need to do is to my decorator, add 1 additional argument. And now I state that the target is CUDA. So essentially, it's going now under the hood to translate the code, the Python code, which is here in this function, to C++ using CUDA under the hood, and it's going to compile it using an appropriate compiler, so basically the NVIDIA compiler. Okay, all of that happens automatically. This is all magic that Numba provides for me, so that's pretty great. And then, of course, the question is, how much performance do I get? And as you can see, it's not too bad. I gain a factor of 2 with respect to the CPU implementation. You might say, yeah, but wait, what's going on here? Because typically, if you talk to people, they promise you GPU speed ups of a factor of 1,000,000. Well, okay, no, realistically, of something like 10. So this is only a factor of 2. So what's going on here? Well, essentially, the problem is, well, there are essentially 2 problems. One thing is, of course, I have to be a little bit careful with my benchmark here, because the first time this function is run, it's also going to be translated into C++, and that C++ has to be compiled. So that's one thing that you need to take into account when benchmarking. You have to be careful that you measure what you want to measure. That's the execution time of your function, and not the shenanigans which are required in order to produce that function in the first place. And that's a one-off, because Numba will actually cache the resulting source code it generates. It will also cache the object file that it generates in order to be used on the GPU or directly on the CPU. But there is another thing as well, and that is, of course, that when I do this in a very naive way, and I think you will agree that this is pretty naive, that there is a written contract in the sense that what Numba is going to do is it is going to transfer the data to the GPU, and it's going to transfer the result back from the GPU to the CPU host memory. Okay, and that is something that is potentially a bottleneck with respect to performance, because you may or may not be aware that typically when you think about performance, one of the things that you definitely have to take into account is data transfer, because it's not necessarily the number of elementary computations which your CPU or your GPU, for that matter, it doesn't matter, that's all the same thing from that perspective, does per unit of time, but it needs data to do that. So transferring data from main memory, so from the RAM of your compute node, to the CPU and to the GPU takes time. There is a finite bandwidth. That's one issue. There is also the matter of latency. So essentially, how long does it take in order to get my data transferred? And that is something that, unfortunately, you need to take into account. So that is something that you also want to minimize. So if you can avoid transferring data from host to GPU and vice versa, so if the data can remain on the GPU because you want to do something else with it, and meanwhile you don't need it on the CPU side, on the host, then don't transfer it. And that's happening here time and time again. So basically that's why we still get a gain of a factor of 2 approximately, but yeah, not more than that. So, okay, what can we do? Well, we can manage data explicitly. And for that, Numba also has a number of primitives, a number of functions in order to do that. So for instance, I can explicitly move my data to the device, and that's quite simple. I just do CUDA to device. Remember, if you go back to requirements, you see that I imported from Numba, I imported CUDA. So that's just to simplify my life a little bit. CUDA is just a module. So that's why you have the CUDA dot to device. Okay, so I explicitly move my NumPy array to the device, and note that again, a lot of things are in fact happening automatically. So X is a NumPy array, and to device properly takes that into account. So a lot of magic is going on here under the hood, which again makes our life a lot easier. So now I can refer to my data on the device, and of course doing computations on it on the device. I can actually use the xdef variable, which I just defined. And then I do something else. Basically, I want the values to go into a data structure, an array, that is also on the device. Okay, now I don't want to initialize that, because basically that is going to be used, this values variable is going to be used to hold the result of my computation. So it doesn't make sense to initialize that at this point. And then I can very easily create an empty array. So this is just memory allocation at the end of the day by using device array. So device array just allocates. And that's very similar to what you know from NumPy. NumPy empty would do the exact same thing, conceptually, of course. So this, of course, is happening on the device, not on in the host memory. Okay, just like you have NumPy empty-like, you have device array-like. So basically that means take the shape of X, take the D type of X, and use that in order to allocate sufficient memory in order to store a similarly sized data set with the same type. Okay, so now I have an additional value out here, which I specify, and that is going to contain my data. Okay, but wait, where did that come from? Well, basically that's again automatic. So that's something that the Numba framework actually provides. So the decorator will make sure that the resulting function is going to have an additional out. Is going to have an additional out parameter, which is essentially literally that in Fortran speak. So basically, it is going to be filled with the result of the computation. Okay, and if I time that, then you see that in fact I get close-ish, okay, not quite to a factor of 10, but it's almost a factor of 10. Okay, so that is quite significant speed up. So we came from 2.5 seconds in very naive Python to under a millisecond, 0.8 milliseconds for the GPU version. Okay, now you can say, well, okay, yeah, that's cool, but let's just do this with NumPy because we know NumPy. So indeed, how much time would the same thing take if we use NumPy? And then, of course, we are on the CPU again. So basically, if you time that, you see that it's 104 milliseconds. So basically, that is quite good, but we still have some gain, approximately 33% on the GPU. Okay, you might say, that's cool. Why is NumPy that fast? Well, essentially, under the hood, it will actually use multiple threads. And this system has 8 physical cores, 16 virtual cores. So basically, it can do quite a lot of stuff in parallel as well. And let's be honest, this is a very tiny workload. So given the amount of work, which is not that much at the end of the day, you can't really expect huge speed ups from GPU. Okay. And of course, it's always useful to check your results. So basically, I'm just computing all the results here, the ones from the GPU, the ones with NumPy, and the original one, and I'm just comparing whether all the results are close. So basically, using NumPy all close in order to see whether my results match, and indeed, they are quite close together. You may have differences between the GPU and the CPU. That may happen because of slightly different numerics. Okay, but of course, order of magnitude and up to quite a number of significant digits, this should be the same. Okay, and then just a plot. Yeah, no surprises here. This is indeed what we would expect from a Gaussian function. Okay, so this was a little warm up. I hope I convinced you a little bit that Numba seems interesting, both on CPU and GPU. Okay, so let's do something different now. Let's compute pi. That's always a nice thing to do. So basically what we're going to use is essentially throwing darts and counting how many darts land on an inscribed circle into a square. So this is a randomized method in order to determine pi. Don't do this at home. It's a very stupid way of computing pi, really. But the reason I want to show you is essentially that I want something that requires random numbers. Because on GPU that takes some care and that's not automatic. So essentially, that is why at the end of the day, when we look at the requirements, you noticed this from Numba CUDA random import this Xoro 128 functions which are used to generate random numbers. But we'll come to that. Okay, first let's consider the CPU implementation as usual, because that gives us a baseline. So how do we compute pi? Well, as I already mentioned, we kind of throw darts at a board. So basically, we get coordinates, x and y, from a random uniform distribution. So basically numbers between 0 and 1, uniformly distributed. So essentially that means that I get a position in a square which is limited in the x direction between 0 and 1, and in the y direction between 0 and 1 as well. And then I compute essentially the distance from the origin, and if that is less than 1, then of course I hit the circle. And then if I just divide the number of hits by the number of tries I had, and I multiply by 4, because I only have a quarter circle, then essentially I have a value for pi. Okay, again, really don't do that at home. It's not a way to compute pi, so it's just in order to use random numbers here. Okay, so I do that for 100,000 tries, and as you can see, I get something that is actually still pretty far off from pi. I just get 3.14, and yeah, then things go south. So basically, I get, if you like, 3, maybe 4 significant digits for quite a number of computations. That's not so very good, but okay. So just to show you, and by the way, note I've compiled this into Numba as well. So basically the njit is just the very simplest way of getting something compiled on CPU. Okay. So in this case, I didn't specify the the parameters of the function type. It's fairly obvious. I didn't specify the result type. Again, it's fairly obvious. So probably nothing much is to be gained there, so I'm not bothering. Okay. And anyway, it's also to show you something else. Okay, so in order to assess the precision, basically we use the function which we need to compute. So that's a higher order parameter. This is a function. Then we have start exponent, stop exponent, and so on. The number of runs in order to do some arguments, to do some, statistics, and then some additional arguments, which I'm going to pass to compute pi. Okay, so basically we create a log space for the number of tries. So that's just orders of magnitude which we skip, you will see. And then for the number of tries, specific number of tries, we're going to compute, use compute pi, whatever that is, with number of tries and potentially additional arguments. Okay, then I store the results. And at the end of the day, the results are returned. Okay. Results are stored in an empty array, etc. So basically, that is nothing fancy is going on here. Okay, so I can execute that, and basically I go from 10 to the power 2 up to 10 to the power 9. So basically from 100 to a billion, and in total I have five runs. Okay, and as you can see, this is the result. So basically, this is the number of tries I have. That's the x-axis, and indeed it goes from 2 to the power 10 to the 9, so basically a billion. And as you can see, it goes down somewhat linearly. So essentially, note it's a log-log plot. So the precision for 100 tries is really, really bad. It's just one significant digit. You probably end up with 3 if you round, and that's great. But even for a billion numbers, you see that you end up with something approximately 10 to the minus 5 precision. So yeah, it's really not a way to compute pi. Anyway, let's turn our attention to more interesting things. And basically that means, how do we do that on the GPU? Okay, so basically I do want to time this as well. And essentially, I want the number of tries to have special value. So basically, you see this number of blocks here and the number of threads per block. Essentially, they don't play any role at this point on the CPU. They will be important on the GPU. But just to compare apples to apples, I'm just using the same numbers in order to do the same number of tries on the CPU as I do on the GPU. So essentially, this is going to be 1024 times 4000, and then times 128. So that is going to be something that is close to half a billion, if my mental arithmetic here is not too far off. And if I time that, I get to 3.25 seconds on CPU. Okay, and that is again using Numba. So basically, I do use acceleration using C++. All right, how do we do that on the GPU? Well, things are going to be a bit more sophisticated here, because a random number generator is something that is stateful, in the sense that in order to compute the next random value, basically you use the state of the random number generator, and then you update that state for the next random number. So that state has to be stored somewhere. Okay. So essentially, if you use single threads like you typically do in Python, then of course there is only a single thread. That thread can happily update the state of the random number generator on the CPU, and no problem. Okay. For those of you who have done some parallel programming on CPU and who have used some random number generators, you might know that also there you need to take some care. Because if you just naively use the, for instance, the random number generator in the STL for C++ or in the standard C library for C or equivalent for Fortran, basically you have to be a little bit careful, because those random number generators are stateful. And basically that means that updating that state is going to make your code sequential. And typically, if you do that in a naive way on CPU, you'll see a drop of performance. What you need to do, if you do that on a CPU, is to make sure that each thread manages the state of the random number generator it's using. So basically, you have to make sure that you have a state per thread. And of course, given that on a GPU, you are going to do something very similar. Each thread on a GPU is going to generate random numbers. It needs to do that independently from any other thread. So essentially, you will need a state per thread. And that's exactly what this function here is going to do. So basically, now we have a function, and it takes, as you can see, as its first argument RNG state. Then it's going to take a number of tries, and it's going to store the results in the parameter which is passed to the function. Note again, I'm using a different decorator here, so a more naive decorator than I did before. I'm just using CUDA JIT, which does a lot of things automatically. Okay, so what am I going to do? Of course, now I need to know which RNG state to use. Okay, this I can determine based on the index of the thread. Okay, and I can get the index of the thread. So many of these functions will be executed concurrently, but each will have an individual value of this index here. And I can get that by using CUDA-grid 1. So that is going to give me that index. And that index I'm going to use in order to use the RNG state specific for this particular thread identified by index. Okay. And this function here, this rather cryptic thing, is essentially going to give me, as you can guess from the name, it's going to give me a uniform float32 value. And okay, you can't know, but this is between 0 and 1, just as the random function would do, or the rand function would do in the Python standard library. Okay, so again, two calls to a random number generation function. And of course, I'm using the state for this particular thread, and that's ensured by getting the index. Okay, apart from that, nothing special. It's the same all over again. Okay, so now, of course, where do these RNG states come from? Because I said, yeah, we need a state per thread, and okay, how do I know? Where does it come from? So I'm going to write a wrapper function, compute by GPU. So this is my kernel. This is what is going to be executed on the GPU, but this one here is going to be executed on the host, and this is going to set the stage. Conveniently, it's going to wrap quite a number of function calls, so that the only thing which I need to specify is the number of tries, the number of blocks, the number of threads per block, which I want. Okay, so wait, what? What are these number of blocks and these number of threads per block? Well, typically, if you do work on a GPU, you think of your work, you divide your work over several blocks. And the block can be one-dimensional, it can be two-dimensional, it can be three-dimensional. There it ends. You only have at most 3 dimensions. And you can choose whether you work with 1 dimension, 2 dimension, or 3 dimensions. So basically that allows you to map blocks onto your domain. So if your domain is one-dimensional, and in this case that would be the case, then essentially a block is just a sequence, an array, a one-dimensional array, if you want, of threads. That's the idea. And each block can use a certain number of threads, and any number will do, but at most 1024. A block size on a CUDA device is limited to 1024 threads. How many threads you take depends a little bit on what you're doing exactly. So one of the things that pays off, I'm not doing it in this particular notebook, but one of the things that pays off is to play a little bit with this number of threads and see which number gives you the best performance. It's not always the case that 1024 would be optimal. Sometimes it's less. It can be 128 in some circumstances. But that also means, of course, we'll come back to that, that if you have a 2 or 3-dimensional block, then basically the number of threads in each dimension, if you multiply them, should be less than 1024. So that's always something to keep in mind, otherwise things go haywire. So, okay, that's my wrapper function. As you see, no declaration, this is just running on the CPU, nothing special happens. So the first thing I'm doing is to actually create these states. And again, that's the second function for this Xoroshiro algorithm. It will create states based on, as you can see, the number of threads I'm going to have in total. And that's, of course, the number of blocks I have times the number of threads per block. Okay, and then I can specify an a seed, and in this case I'm just seeding with a random number, something between 0 and 100,000. Okay, you can of course fix this to a particular number for reproducibility and so on, so please note this is not reproducible, and of course in this particular case I don't care about reproducibility, so I can happily put some random value there for the seed. This is of course just a random the Python random number generator which is going to be used. So all of this seed production thing, this part of the code, that happens on CPU, on the CPU. So that has nothing to do with the GPU. So this basically sets the stage. That makes sure that on the device there is going to be an array of data structures that can contain a random number generator state. Of course, I have used the word random number generator. You know that what I'm talking about is pseudo-random number generator, but yeah, that's just a lot of effort for something that is not particularly adding much information here. Okay, so then of course I need my results. So again, I'm going to create a device array. And in this case, I'm very explicitly specifying the shape. That's here. So I've got an array that contains one element per thread. And the number of threads is again the number of blocks times the number of threads per block. Okay, and I also specify the d-type, and as per usual, I specify a float 32. Okay, then I actually call my kernel, basically compute by kernel. So I specify, in this case, the number of blocks and the number of threads per block. Oh, wait, this is interesting. What happens here? So let's have a look again at compute by kernel. So that's this guy here. So this is something that I compiled for CUDA. Okay. And now in this case, I'm telling the CUDA device explicitly how many blocks and how many threads I'm using. But this is a very weird notation in a sense. So you might say, okay, what is this? Because this looks like I'm sort of using a list or an array or something like that. What are the square brackets things doing here? Well, this has nothing to do, absolutely nothing with indexing. So it's not as if I'm taking an array element or something like that. There's absolutely nothing to do with it. The point here is essentially that you can overload this index function with anything you want. So that's one of the Python's dunder functions. And here it has been abused in order to sort of mimic classic CUDA notation. Because if you would do that in CUDA, the notation would be a bit similar. You would have compute by kernel, and then 3 times less than your number of blocks, your number of threads, closed by 3 times larger than. So that would be classic CUDA. And in this case, well, I'm not, but the Numba developers have decided to implement this using the dunder function, which typically gives you the index into some data structure. So that's essentially what is happening here from a Python perspective under the hood. But basically from the perspective of a GPU device, what I'm saying is how many blocks and how many threads per block I want to use. And this determines how my kernel is going to be executed. Apart from that, I pass the number of RNG states, sorry, the RNG states themselves rather, sorry, and then I specify the number of tries, and of course, each thread only has to do the number of tries divided by the number of blocks and, well, the total number of threads essentially. And remember, given the definition, that would have been 1024. And I also specify the results. Okay. Wait, then there is something else which is curious here. So basically you see that there is this CUDA synchronize. What does that mean? Well, essentially, when I launch my kernel, it's going to be executed on the device, and meanwhile, execution on the host can continue. So, given that the next statement is in fact computing something using def results, I'd better be very, very sure that before I do this, before I compute this sum, that actually the results are there, that I have my results. So that's why the CUDA synchronizes here. So basically that tells us, okay, wait at the host until all outstanding GPU kernels have finished their work, because only then that result is safe to use. Before they've finished computing, I can't really use dev results, because part of them would not be there potentially, very likely. So that's why the synchronize is there. So that is something that you really, really shouldn't forget, that you are really sure that before you use data which is being produced on the device is actually done and ready for use. So don't forget, this is a pretty important aspect. Okay, then we can use our wrapper function as before. So basically compute, not the wrapper function, the compute by GPU, which we just defined with the number of tries, number of blocks, etc., etc. And as you can see, I get something quite reasonable. I get 3.14, 1.5, okay, and then things go south. I should have a 9 there rather than the 4, but okay. As you can see, reasonable result, no surprises. Okay, so how fast does it perform on the GPU? So basically 119 milliseconds. And if memory serves, it was quite a bit over 2 seconds on the, well, it was actually 3 seconds on the CPU. So basically it's quite a bit faster. Okay. However, am I comparing apples with apples here? There are a few things. Let's quickly go back to the CPU implementation. All of this is, sorry, that's not the one. All of this is pure Python. Okay, so X is going to be a Python float. A Python float is 8 bytes. That's a float 64 under the hood. So, this is not really, really fair. So, if you're comparing things, it's something to keep in mind. Okay, another thing is I'm using random here, so the random function out of the random module in the standard Python library. And in my CUDA stuff, I'm using this Xoro method. And then again, there might be quite some differences, because not all pseudo-random number algorithms are created equally. And Xoro is not a bad algorithm, but it's not as good as many other algorithms. So this is something that has been really developed for use on GPUs. It performs very well because it is rather simple to implement. So that is also something that you have to keep in mind. If you look at the statistical properties of Xoro, whether that would actually be up to scratch with what you require from a random number generator. In this case, no one cares, so it's all fine. But if you rely on the statistical qualities, so the distribution of your random numbers, the quality of that distribution, if you care about correlation lengths, then this is something to very carefully check whether Xoro is actually going to give you that kind of performance rather than the let's say GPU performance, so basically the time it takes to execute. So bear that in mind. I'm sort of comparing apples to oranges here. But anyway, let's have a look at the precision graph. So as you can see, this looks somewhat similar, but yeah, it's not quite the same. So you don't get this very linear thing. But remember, we only have 7 digits of precision because on GPU I've been using float32, and I'm actually computing quite a lot of random numbers. So basically, yeah, I should get something slightly different. But still, I get a precision which is similar. So something like 10 to the power of minus 5, even a bit better for a billion numbers. So it's reasonable. Okay, let me check the time. Okay, I think I'm doing well. So this is interesting, and mainly I gave you this example not so much to show you how to compute pi, but of course to show you that you can do random numbers on GPUs, that you need specialized algorithms in order to do so, and that, for instance, Numba, but also other libraries, will have quite a choice of algorithms. Okay, let's do another example. And in this case, that's the Mandelbrot set, which you are all familiar with. I like it because you get pretty pictures, and pretty pictures are always nice to have in training sessions. Okay, so again, we're going to, if you look at the sentence here, we're going to do that once more. That's basically because it's a bit of a running example when I give trainings about high performance and high performance computing and Python. This is a running example for all kinds of things like Cython and even multiprocessing, etc., etc. So the pure CPU work, also NPI and so on. So basically, that's why I like this example. Anyway, and why there is again in the sentence. Okay, so again, we're going to be a bit more specific here. So basically, I'm going again to specify the parameter types for each parameter of my function, as well as the return type. So in this particular case, we have z, which is basically a complex number. We have c, which is a complex constant. And we have max steps, which essentially could be whatever. Just for convenience, I've made it an int32. In fact, it could have been a smaller type, but I don't care because, as you will see, it's not particularly important. And what is going to be returned is a uint8. So let's first talk a little bit about complex 64. So you might say, okay, 64, so that 8 bytes, so that's nice, that's double precision. Well, no, because it's actually indeed 8 bytes, but it's going to be 4 byte for the real part and 4 byte for the imaginary part. So this again is single precision. Again, that is not a limitation of Numba or whatever, it's just to fit my hardware on which I develop this training. Okay, int32, well, that's just your average integer, basically 4 bytes, so that goes from 2 to the power, from minus 2 to the power 31 up to 2 to the power 31 minus 1. So yeah, nothing special. uint8, okay, so what is that? Well, the 8 means 8 bits. Okay, so that's not that much. And the u means unsigned. So this is an unsigned 8-bit number. So that can store values between 0 and 255. Okay? Why do I do that? Well, basically because at the end of the day, the number of steps which will be returned is something that I want to plot on a heat map. And basically, that means that I have 256 levels of gray. So that's why I restrict it to a uint8. There's no mathematical reason for that, just a practical one, because I just want to make sure that I can plot this nicely. Okay, so basically, I'm going to iterate, and this is just for a single complex number. So I'm going to replace that in each iteration by its square, and I add that constants which I also pass. And each iteration, I increment number of steps by 1. Okay, I'm doing that for less steps than max steps. Okay, That's not particularly interesting. But also, as long as the norm of the complex number is less than 2. So note that I apply a classic trick here. So I said, okay, the norm of z should be less than 2. Okay, but yeah, there is a function for that. But of course, that implies a square root. The square root is slow, so I don't want the square root. So essentially, what I can do is just square both sides of my both operands of my less than comparison. So I get the real part squared plus the imaginary part squared, and then of course that should be less than 2 to the power 2, so basically less than 4. So this saves me some unnecessary computations and will actually speed up my computation considerably, since square root, as I mentioned, it's a slow operation. So if you can avoid doing square roots, if you can avoid other transcendental functions, it's definitely a good idea to do that. Okay, simple tricks, nothing special. Okay, then this is going to be my kernel, and as you note, it starts CUDA, so that's going to run on the GPU. Okay, then we need our array. So we are going to do that for many z values, and those z values have they are on a grid, if you like, and that grid has real values typically from -1.8 up to 1.8, and an imaginary part from -1.8 to 1.8, so essentially it's square. And basically I'm generating that here. So in this case, it will be a 1000 by 1000 grid. So I first generate all the real parts. So basically just the lint space. The float type is 32 as usual, and values range from -1.8 to 1.8, and I've got 1000 of them. And similar for the imaginary part. So then I can create two two-dimensional arrays, one for the x values, one for the y values. And basically I can do that using the NumPy mesh grid function, and that is going to give me two-dimensional arrays. Okay, so the uppercase x is a two-dimensional array, as is the uppercase y, and now I can add those. And of course, for the y, that's intended to be the imaginary part, so I multiply it by essentially I, if you want, or in this particular case, as Python uses this notation, j. Okay, so that's more engineering notation than it is science notation, but yeah, that's how Python works. Okay, and so basically z is going to be a two-dimensional array as well. As you can see, its D type is complex 64, and that's indeed what we want to have here. Okay. The shape is 1000 by 1000, as we expect. So basically that means that Z00 would be -1.8 plus I -1.8 minus I 1.8. Okay. So then we need C. Again, we have to take care that that is a complex 64, so not a Python complex number. And I'll just take this particular value for it, whatever. Okay, then the maximum number of steps is simply 256. And this is essentially why I'm using this int 32 here. Okay. So then we do the computation on the device. We get our image, our specified set, C, and the maximum number of steps. When we do that, the result is a ND array, so that's good. The D type is uint 8, so that's indeed as expected, and the shape is as expected. So, whoa, this is pretty cute. I created my kernel, and that just took a single complex number and I just apply that to a two-dimensional array, and I get the right thing. And that is pretty impressive. That was very easy. Okay, and we of course can visualize this, and then you get a nice plot, which looks like this. It's a fractal, so always a big success, looks nice, and so on. Okay, all right. So in the repository for this training, you would also find an implementation using PyCUDA, so a different framework for doing computations on GPU. And yeah, if you would look at that, the Numba implementation is considerably simpler. I'm not going to compare here to PyCUDA. Feel free to check the repository. Okay, so of course that's nice. It works great. It looks good. But what's the performance? So as usual, we do the same thing on CPU. So essentially same thing, vectorize. Target now is not specified, so it defaults to CPU. Apart from that, this implementation is identical. Okay. Here is the same implementation again, this time for CUDA. I don't know why I repeated it, probably not to get confused. But anyway, so I've Mandelbrot CPU, Mandelbrot GPU. I create my data. Now it's going to be larger. As you can see, rather than 1000 by 1000, now it's going to be 10,000 by 10,000 to make it worth our while. So basically quite a bit bigger. Apart from that, data preparation is the exact same. We have the exact same constant and so on, the same max number of steps, and then we can time. So for the CPU, we end up with 683 microseconds. So I'd say that's quite good. And then if we time the GPU, we get 552 microseconds. And that is not particularly impressive. Basically, yeah, that's like 20% better. And yeah, this was really a pretty large matrix. So, okay, but yeah, maybe it has to do with data transfer. So, okay, let's put the Z matrix on the device first. So I'm going again to use CUDA to device, and we get a device variable. And also for the result, I'm going to do the same thing. So basically, I create a device array with the same shape as Z, and with, in this case, np-uint 8. In this case, of course, I can't use device array like, because obviously the shape of image will be the same as Z. That's not the point, but of course the type will be different. Remember, Z is complex 64. I want here a uint 8. So in this case, I just have to do it this way. Okay. And if I time that, you see, indeed, things improve. So basically, we go down from 550 milliseconds down to 350 milliseconds. So, okay, it's an improvement. We're almost at a factor of 2 with respect to the CPU. Okay, but yeah, somewhat disappointing, I'd say. Do we get the right result? Yep, we actually do. So again, we have this nice looking fractal. You might say, okay, how do you know it's the same? Well, typically, if you mess up, the picture will really, really look bad. So essentially, that's why I know it's okay. You could do a more formal way. You could do this more formally. You could just use np all close, etc. But okay. Right. Well, right. I don't know. I'm underwhelmed by a factor of 2 for something that should, in fact, map really, really well to GPU. So, what's going on? Well, one of the things, if you just go back to this kernel, one of the things you might think is okay. What I'm doing here in this CUDA thing Well, essentially, it's just computing for one Z value. So at most, it is going to do a fairly limited number of computations. It is going to do a square per iteration. Well, essentially, it's going to do 3 squares per iteration, because I also have to check the condition each time. And then there are a few additions. So yeah, it's not that much. So 3 multiplications, an addition, so that's 4. Forget about the integer because that's a different thing. So basically 4 elementary operations per cycle, per iteration, and I've got at most 255 iterations. So that's not a large number of computations, that's 1,000 computations. Okay, but this function is going to be executed by a thread. So basically that means that I have a thread which does only 1,000 single precision computations. And I've got 10,000 times 10,000, so 100 million of those threads. Oh, that's great. So I'm creating 100 million threads that each do 1,000 floating point operations. That's not so very good. Okay, actually, I should say it's not quite true because actually z squared here is more than one multiplication, but still, you see where it's going. Even if it's 1,500, I don't care. At the end of the day, it's very few computations with respect to the number of threads which is going to be created. So that is unpleasant. That means a lot of overhead, because if you create a thread, of course the device is going to have to do quite a bit of work in order to create that thread, manage that thread, finish that thread, collect results, blah, 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 blah. It will all be quite a bit of work. So, 100 million threads, 1,000 operations, 2,000 operations if I'm very generous. No, that is probably not a good idea. So can we do better? Yeah, we can. What we can do is say, well, okay, given that I don't want 100 million threads, I want to reduce the number of threads and increase the work per thread. So what can I do? And I can use threaded loops. Okay, so let's do another implementation. And not that much changes. So the computational kernel is still the same. That's this guy here, our while loop. Okay, so this didn't change at all. This is just the exact same implementation. Okay. But yeah, what I do is I determine the grid coordinates. So in this particular case, I want a two-dimensional grid because my problem is two-dimensional. Okay, it's actually not two-dimensional. In a way, all these computations are independent, so I don't need to consider this a two-dimensional problem. In fact, it's happily a two-dimensional problem, a one-dimensional problem. The reason I'm using two dimensions is mainly to show you. So essentially, in this particular case, I want the grid coordinates. So basically, I want the x and y grid coordinates. Remember, we have these blocks. Well, this is the index into that. And then I also want the stride. So basically, how large are my blocks? That's going to be in x stride and y stride. And now I do a number of iterations. So basically, I'm going to iterate over I and over j. And those are just have to do with the shape of set. And I'm going to do that in strides of x and y. So essentially, a single thread is no longer going to do no longer going to compute on a single value of set. It's going to compute on multiple values of set. Okay. So that also means, of course, that I have to take into account the number of steps here. That's no longer a number, that's now an array. And of course, I also need the value of z to compute with. And just for convenience, not to be forced to write zij everywhere, I've just assigned this to lowercase z just to simplify notation. Okay. All right, so I'm going to choose a total of 512 blocks. And in each thread per dimension, I have 16 threads. But remember, these will be two-dimensional blocks. So that means that I have 16 times 16, 255 threads per block in this case. Okay, so the number of threads per block is indeed going to be 16 squared. All right, n is going to be the number of blocks times the number of threads per dimension. I'm going to prepare my data in such a way that everything fits nicely onto this distribution of threads. So basically that's why we have the multiples here, and I just prepare my x and y, and at the end of the day my z as before. Okay, and just to show you, in total we will have 8,196 in both dimensions. So basically that would be 2 to the power 14, I think, if memory serves. So basically that is going to be a lot of numbers. 2 to the power 14, so that's 2 to the power 28. So yeah, that's somewhere around, I don't know, whatever, close-ish, but not quite, 64 million or something like that. Anyway, again, I define my constant as usual, maximum number of steps, nothing changes. I'm going to create, I'm going to put z on the device, and I'm going to put a result on the device. So note that this is a little bit different. In this case, I'm actually initializing my result. Why? Well, if you look at the implementation, you see that I shouldn't have actually, because there is an equal to 0 here. So in fact, I shouldn't have done that, but okay, we can live with it. So basically, I also put the result onto the device. Okay, then I launch my kernel, but now, of course, I have to do it the right way. So basically, I have to make sure that the Mandelbrot kernel is launched to run the number of blocks I specified. So don't remember offhand what it is, 512, and that the number of threads per block is indeed 16 squared. And then I just pass on the appropriate values for the z values on the device, the device result, and so on. Okay. So let's see whether it works. Always a good idea to verify if you change stuff that it still produces the proper results. Notice, by the way, that I'm using dev results copy to host. So I make sure that before I actually use dev results, that this is copied to the host memory. I have to do that explicitly. And as you see, this is again the same figure, so that looks nice. Okay, so what does that mean in terms of performance? Well, basically, if I execute the kernel that way, you see that I go down to 16 milliseconds. And remember, originally I had 300 and something, 380 or something, don't quite recall, but basically this is a huge performance gain. That's a factor of somewhere around 20. So that is quite considerable. So the message here is that in fact you have to make sure that your threads have enough work to do to offset the overhead involved in creating threads. So naivety here is really pretty lethal with respect to performance. It's really a factor of 20. So that is quite considerable. Okay, so what else can we do? Well, can we still do better? Well, yeah, in fact, we can. Because basically, what we haven't paid attention to is the underlying hardware that much. Okay, we have talked about threads and giving them work, that's great, but there is also the aspect of memory. How is that organized in GPU, and how does that impact how we do stuff on GPUs? Well, basically, you will know that on a CPU, if you want performance, you have to take a little bit care of how, if you do multi-threaded programming, of how you access your data. Because what you want, of course, is that the caches of your cores are used optimally. So basically, that means that you want to make sure that each thread accesses data values that are consecutive in memory, so that if those values are transferred from the memory to essentially to your core, they pass through several layers of caches, and basically that your level 1 cache is filled with cache lines that hold consecutive values on which you operate one by one after the other. So that's essentially the idea. So on CPUs, it is also quite useful to make sure that you're familiar with the data layout of your data in memory, and also that you are aware that accessing your data in a certain pattern will be more efficient than if you do that using another pattern. And essentially the same applies to GPUs. Why would it be different? So on GPUs, you think in terms of warps. So basically a warp is a set of 32 threads that are executed in one unit. And basically, they are going to be the important factor here. So for AMD, a warp essentially is a wavefront. So they use different terminology, but it's the same concept. So what you basically want is that you get consecutive values. So basically, you want to make sure that the index in your loop is such that memory access is appropriate for usage on a GPU. And that's called coalescing memory, or your data should be coalesced. At least on my screen, the sentence drops out. I'll try to decrease this a little bit or move it. So basically, that's the idea here. So essentially, what you have to make sure is that if you access the number of steps and you access the Z values, that you do it in the appropriate order. So basically nothing changes here except these two lines here, and of course this guy here. So the only thing which has changed here is swapping I and J index. Okay, and then you have to time that, and in this case, actually, here the problem is that my benchmark probably is wrong, and as I told you, I'm not really a very big fan of rerunning it. But basically, my benchmark here is not particularly okay. The number here doesn't fit. Normally, you would see that the performance again improves quite a bit. Here the numbers are off because there is a factor 7 here between the slowest and the faster runs. So basically, this benchmark is not okay. But if you divide the maximum, then you see that actually this will be lower if you do it properly. So again, memory access pattern matters. They matter on CPU, and they matter on GPU as well. So that can give you a factor of 2 to a factor of 5, depending on the problem you are trying to solve. And of course, again, on the size of the work done by the individual threads. Okay, so how do you figure out the data mapping? Well, you can explore that a little bit in a pretty straightforward way. How do these things map? So basically, I write a small CUDA function, that's a CUDA kernel, that is really not that impressive. It is just going to take the index of a particular thread, and it's going to get the grid coordinates, again, the grid indices from the device, and they're just stored in X and Y. And what we're going to do is to just in a XY, we store the index. So it's just a very simple function in order to see what is mapped where. Okay, so I consider a 16 by 16 grid, and I use a single block. So basically, this again is two-dimensional, so I just have a single block here of 16 by 16 threads, and it's just an int 32. I don't really care what it is. And I also have just 16 threads per block. So this is really quite straightforward. And if I execute that, you notice I specify the number of blocks, the number of threads per block, and I specify that on A. And you see immediately that Numba is kind enough to tell you, well, are you sure that what you're doing is a good idea? Because it says, okay, there is a performance warning. The grid size of 1 is going to result in GPU underutilization. Okay. Of course, here it really doesn't matter. But in general, it is actually a good idea to have many more blocks than you actually have. Well, basically, in total, you would use many more threads than you actually have physically available on your device. So that's something that, if you come from a CPU background, sounds very counterintuitive, because on a CPU, it's pretty clear. You run as many threads as you have physical cores. That's it. That's gospel, except if you're doing weird things with I/O or something like that. But apart from that, for computation, it's quite simple. A thread per core, 1, that's it, end of story. Okay? Maybe on very recent hardware, 1 per virtual core, but okay. So that's the typical rule. So that does not apply, absolutely not. On the contrary, on GPUs, you have many more threads than you actually have physical GPU cores to run them on. And that has to do with management and with the overhead of managing your threads. So essentially, in order to keep all the hardware busy, it's quite useful to have many more threads than you have cores. And that is exactly what this warning is about. So basically it says, well, okay, you have very few threads, you use almost nothing, so this is very low occupancy. So it's not going to be happy with that. It's just a warning, so I'm going to totally ignore this because it's not the purpose here. Performance is not my purpose. What I want to see is how the threads are mapped to the data. And so basically this is what you get. So essentially this is row by row. The index is mapped to the entire row of this data. Okay, so again, row versus column, sum and memory access. So this is essentially similar to what we have already been talking about in the context of the Mandelbrot set, but here illustrated a little bit differently. So we're going to consider a large number of values, so 2 to the power 14. Okay, that's not that large, that's 8,196, something, I think so. Basically I want 128 threads per block, and the number of blocks in total is then the n divided by the number of threads per block. Okay, so I have 128 blocks and I have 128 threads per block. Okay, now I'm going to create an array n by n, just a uniform floating point, 32 bits as usual, and I'm going to move that to the device. And I'm going to compute the sum. So basically that is again for the results. So I'm creating an array which is initialized to 0, and it just has n elements, so it's a one-dimensional array, again float 32, and I'm also putting that on the device as well. Okay, that being done, I can write a small kernel that is going to take a matrix A, and it's going to take a one-dimensional vector or one-dimensional array sums. Okay, again, of course, I have to give it some work, so I'm not going to compute the sum of a single array element. I'm actually going to compute multiple. So basically, I'm iterating over quite a number of row elements of A. So index is going to be my column, my row index, J is going to be my column index. So essentially, I'm iterating in my kernel over rows. Okay, and then I'm going to assign that row sum, which I compute here, to sums index. Okay, so I launch my kernel as usual with the given number of blocks, the given number of threads per block. I have the A on the device, I have sums on the device, and of course, since I want to make sure that this is done, again, I could asynchronize. Okay, and then I can get it copied to the host, and as you can see, this is the result. So basically, I get something which is close to 8,196 because I had a random distribution between 0 and 1, and essentially that would be the expected value. No surprises there. Okay, of course, I'm not interested in the results. This is just verification that what seems to happen is the right thing. So if I time that kernel, as you can see, it takes 10 milliseconds. Okay. Note that I add a CUDA synchronize here. So basically these two statements are executed each time, because otherwise I would launch multiple kernels and yeah, they would interfere with one another. So I really want to make sure that one kernel is completely finished before I launch the next kernel. Hence the CUDA synchronize here in this time it magic statement. Okay, so 10 milliseconds. Now we do the same thing, well, almost the same thing, but basically rather than summing over the rows of the matrix, I'm summing over the columns of the matrix. So same thing, except that index and the for loop index have been swapped here. Okay, so again, we can verify. Again, we get something which is close to 8,196 for each element. So yeah, seems okay-ish. And if we do the timing, you see that we get 6 milliseconds rather than 8 milliseconds, than 10 milliseconds. So again, this is an illustration that your data access pattern really matters with respect to performance. And it's quite useful to check whether you have the right one, unless you're really, really sure and have a bit of experience and know which way to go in order to compute your sum. In order to access your array in such a way that it's optimal for this device. Okay, so yeah, just two illustrations of essentially the same thing. Okay, last topic about Numba is essentially device functions. So all the functions which we defined up to this point were in fact kernels that could be launched from the host. What we can also do is define functions that can only run on the device, and those are, in CUDA speak, typically called device functions. So basically, a device function can be defined very simply in Numba. You just have the usual decorator, CUDA_JIT, but now you specify the optional argument, device is true. So this distance function, which I have here, is being compiled under the hood again to a C++ implementation, and it will be compiled in such a way that only code for GPU is generated. Okay, so why would you do that? Basically, if you have these kind of helper functions in a way that you are sure will only be executed on the device, it's better to not overload your executables and your libraries with code that's not going to be used anyway. Also, optimization can be a bit more aggressive. So essentially, if you don't need it on the host, just make it a device function. Okay, so then we create a bit of data. Essentially, here I'm doing lots of permutations of arrays, well, between 1 and 10 of 10 elements. So basically, I'll have quite a number of permutations here. And in this case, the D-type is int64. Okay. So, what am I going to do? I've got my number of threads per block is 128, and is going to be 10,000 times the number of threads per block. So that is going to be something around 1 million total. Then I've got A, and that is random numbers. N random numbers, so basically 1 million random numbers between 0 and 1. I've got A and B, and then the expected value would be the square root of these two here. Okay, then I create an array to store results in, and again I use just a NumPy array, which is just allocated, not initialized. It has the same shape and the same D-type as A. I'm using empty like here. Okay. So I create a distance kernel. So this is something that I can launch from my host. That is that can be launched from the host. So it's just add CUDA_JIT as a decorator. It takes A and B, and it takes an out argument. Okay. So basically, I get the start and I get the stride from grid and grid size respectively. One means it's one-dimensional, so this is going to be numbers, and then I range from start to the end by stride. Okay, and I store the distance between AI and BI in out I, and notice this is the device function here. Okay, so if I execute that again, I get a warning for something. Again, it's warning me in this case for what? Again, a performance warning. There is indeed going to be copy overhead because I didn't store A and B on the device. I'm relying on Numba in order to do the transfer for me. And in this particular case, it is going to be unhappy because A and B and out are going to be transferred, although A and B are not going to be modified. So that's why it's not particularly happy. It's also not particularly happy because out is a NumPy array. It lives on the host. So yeah, it's going to be transferred to the GPU anyway. So yeah, it's not going to be particularly happy with that. So that's why you have the warnings. As such, it doesn't matter that much in this particular case for this particular example, because what I'm interested in is just showing you the use of this distance device function. But again, don't do this at home because this is going to be slower than you hope for due to the extraneous data transfer incurred by using NumPy arrays and forcing Numba to do synchronization and transfer after the kernel has finished. Okay, and then of course what I want is to test whether these arrays are almost equal, and indeed that would be the case, unless I cheated because the output is missing. But yeah, it's an assert. So basically, if the comparison succeeds, then there is no output. If the comparison would say, okay, one element of out is different from another, then you would actually get a warning printed, an error that the assertion failed. So that's why there is no output. So no output for an assert is of course good. Okay, so I hope this gave you a little bit of an overview of what you can achieve on a GPU, and also a little bit of a feeling of where the, let's say, the pitfalls lie. And you may argue, yeah, okay, but this is specific for Numba. Well, actually, no. Whatever you do on a GPU, the same principles will apply. You will always have threads. Threads will always need work. If you give them not enough work, it's going to be slow. So yeah, that's the general principle. And it doesn't matter which particular framework you use, whether it's Numba, PyCUDA, or you name it, it's always going to be the same issue. Also, with respect to data transfer, if something need not move from host to device or from device to host, just leave it where it is. Transferring it takes time. It takes bandwidth, it takes latency, so it's going to slow down your code. And if that happens in a loop, that may accumulate to considerable performance loss. So that's also a very general principle. Also, the principle of coalescing your data is again totally independent of whatever framework you use. If you, even if you use something like PyTorch, tensors, or TensorFlow tensors, again, if you have the wrong access pattern, it is going to significantly slow down your code. So all these principles just apply for any framework you can potentially use. Okay, what I do want to tell you in addition is that I have been showing you mostly, well, let's say the CUDA part of this, but you might argue, okay, that's nice, but on Lumi, for instance, we don't have NVIDIA GPUs. There are AMD GPUs, so what about ROCm? Well, no problem. Actually, Numba also supports ROCm. I don't have examples because I don't have easy access to AMD GPUs, but basically you will see the exact same structure in the documentation as we have been following more or less in the slides. And if you compare to the CUDA part of the documentation, the structure is the exact same. So here is documentation on how to write kernels, which is of course very similar to what you would do on CUDA devices. Here it's for ROCm devices. There is also a bit of a terminology switch which you need to make. I've given you one example. A warp in CUDA land is called a wavefront in AMD land, and there are also other differences, like a block is a group, etc. Sorry. yeah, a block is a group, a grid is a grid, etc., etc. So there are differences in terminology, but the underlying architecture is very, very similar. So again, what I've been talking about specifically for CUDA here also applies to AMD ROCm. So basically, here you can see how to do that. And just to give you an idea about, for instance, data transfer, let's go here. So essentially what you see is that CUDA is replaced by ROC, and that's kind of it. If you ask me, okay, why? Because if this is the same anyway, then why didn't the Numba developers just abstract away from this and let you configure it somehow upfront and then all the code remains the same? I don't know. I don't know what drove their decision to split the namespaces this explicitly, and that they didn't try to come up with something unified. Most likely because there are things under the hood which are too different in order to do this safely. That would be my guess, but I'd have to look carefully at how that would work. Potentially talk to the Numba developers or to people who are more familiar with HIP than I am. So basically, that would be a good answer to that question. Okay. Perhaps just for comparison, because I mentioned PyCUDA, so maybe let me show you the corresponding Mandelbrot code for PyCUDA. So that would be here. So that's a little bit GPU attributes. Let's not go there. So concepts are quite similar. You also see that there is a way to get your data to the GPU. In this case, there is a different data type, GPU array. So essentially, and then you have kernels, and your kernels in this case are, as you can see, Python objects, and you have them in different how should I say, with different functionality. So basically, this would be an element-wise one. So basically, that gives you a very easy way to use it element by element. But one of the differences, as you can see, is that essentially you're not writing Python code, you're writing C code. So that is a difference. Your kernel is in fact defined in terms of strings, and those strings are C. So yeah, it's a different approach. It is, I would say, a bit more low level than Numba, the Numba approach. So there are quite a number of examples here, and at the end of the day, here is the example for the Mandelbrot set. So as you can see, my entire code is in fact C or CUDA, depending on how you want to formulate this. But basically, this is the way to do that in CUDA. Of course, this is similar. So essentially, the CUDA has its own type, by CUDA something something. So you also specify the signature. That is somewhat similar, but note you need to know what's a pointer and what isn't. And then you just write straight C code or CUDA code, depending on how you want to formulate it. But the graphs which you get are as pretty as the ones with Numba, so in that respect, it's the same. And then you have a whole family of kernels, ranging from very simple for the element-wise to a little more complicated for the reduction kernel. And then you have a source module, which basically means just write a string with CUDA and that's your thing. So that's just to give you a different perspective on GPU programming. So I would say PyCUDA is very nice for you if you already know CUDA, because what you are writing is at the end of the day CUDA. So yeah, it's a different approach. If you just need to do let's say, matrix computations, vector operations, and so on, matrix operations, then of course consider just using PyTorch or TensorFlow, because that will give you a very efficient implementation for that. Okay, I would suggest to conclude here, that there is time for questions. So
yeah, I think thank you so much, Geert, for this thorough introduction to Numba. Actually, I was not aware of Numba, so thank you so much. And we actually have two questions already in the
okay.
chat.
Mhm.
And from the first one is from Gabriel, and I think it is regarding the initial part of Numba,
Okay.
where you actually talked about the part where you put data inside of the GPU,
Mhm.
and you're assuming that the GPU actually has memory enough, large enough to put all the data.
Exactly.
But what happens when there's not enough space? What are the tricks, and how we can actually manage the amount of data that's going inside the GPU?
So basically, Numba is not going to help you. That's something that you will have to do manually. So you have to be aware of the memory restrictions, so the memory capacity of your GPU. That's pretty clear. You can't move more data there than there is storage space for. So on modern GPUs, you typically have at least 32 gigabytes, 40 gigabytes, 80 gigabytes, depending on how much money you're willing to spend on a compute-capable enterprise-grade GPU. But that is it. So if your entire data set doesn't fit into that, it's up to you to chunk it. So you would have to try and decompose your computation in such a way that you work on tiles. And Numba is not going to do that automatically for you. Of course, there are frameworks, but not so much for Python, I think. But for instance, for languages such as C++, you have libraries for linear algebra. So then we're talking really linear algebra operations, which can in fact deal with tiles automatically. So basically that means they will decompose a linear algebra computation into subcomputations that each fit into the memory of your GPU, and assemble the whole thing in host memory on the CPU part. So that's basically the idea. But here you're actually on your own. And if you're not doing something like linear algebra, again, you will be on your own. That is a hard restriction. Essentially, it's the same restriction as you have on CPUs. So out-of-core computations on CPUs are also non-trivial. And there is some software to help you with Python, for instance, DAS could do that for you in part. But still, it's for GPU, as far as I know, it would be a manual process.
Yeah, that's actually. But would you like be able to work with Numba like in a batch series? Like you really shard your data and work in batches, or
Yeah, you
you
can do
would
that.
need to use
You can do
another
that.
library? You can do
No,
it, okay.
you could do that, but it would be sort of manual work. But basically, yes, you could ensure that the kernel is finished before you move the data and so on. And you could even overlap that because you launch kernels asynchronously. So basically, that means that while your kernel is running, you could actually already start to deal with your data. You could overlap data transfer and computation potentially, just like you can with other CUDA or with other GPU programming frameworks. Let me put it very generally that way.
Okay, maybe we can pass for the second question, and we have the third one actually, and it's from Choran Yu, and it's asking what's actually going under the Numba API, and is it using managed memory or doing implicit copying? I think you talked a bit about it, but can you clarify? Yeah.
So what's going on under the hood is for Numba in general, it's going to generate C++ code. either without CUDA if you're targeting CPU, either with CUDA if you're targeting a CUDA device, or with HipCode if you are targeting AMD, so ROC. So basically, that's what's happening under the hood. With respect to memory, so yes, you can do quite a lot. It's mentioned in the documentation. So okay, I'm going to switch to the CUDA documentation because I'm not entirely familiar with the AMD terminology. Similar concepts, but again, they call things differently. So let me try and find the part I'm in fact looking for. Wait. Where is it? Random numbers, memory management. Yeah, that's it. So basically, you see map memory, etc., etc. So shared memory, etc. So basically, it allows for that. So you can specify things in the API in order to pick the memory mode that you want to use here.
And there's also the shared memory, right?
Yeah,
it's possible
exactly.
to share. Okay.
Yeah. Whether or not that's a good idea is, of course, open to discussion. It makes your life easier as a programmer, but it's not necessarily the best for performance. I don't know how Numba is doing, but yeah, people are wary of it in different contexts. So, okay, I don't know.
Yeah, I think. And two more questions actually. And one is regarding the overhead that launching the kernel in Numba may have, regarding also PyTorch. And if you have compared to raw C++, the kernel launch.
Yeah. So your initial kernel launch is going to have significant overhead because at that point in time, your code is actually going to be generated. So that will take some time. But of course, that's only the first time. And then after that, it will actually be quite performant. And of course, then things depend. Because what you are doing is you are running C++ code that has been compiled with a C++ compiler. Okay, so if, and that's a very big if, the code that Numba generates is equivalent or the same as you would write by hand in C or C++, then of course it should be the exact same. Once your kernel is safely on the device, etc., there shouldn't be a performance difference. But of course, that means that you are relying on Numba to do the correct translation to performance C++ code. So that applies both on CPU and on GPU. That's the exact same assumption you make, that Numba does a good job of translating Python code to C code. That's the underlying assumption. And typically it's not doing a bad job, but if I really wanted to make sure that the right thing happened, well, then perhaps something like PyCUDA is a better idea, because I just write my own CUDA code and I just use Python as a wrapper. That's it. But under the hood, it's going to be exactly the code I want, which might be better or not than what Numba generates. I mean, if I mess up, Numba might do better. But yeah, you see where I'm going.
Yeah, it makes sense. I think only if you are truly CUDA programmers that will actually write CUDA as a baseline. But actually, on that point, in the last question that we have here is you talked about PyCUDA, but how does actually Numba compares with CuPy and NVIDIA Rapids, which are most updated and so on?
Yeah. So basically, PyCUDA is indeed older. That is definitely true. So CuPy is indeed more recent. Let me see. I think I have material on it even in my training repository. I'd have to check, but let's check for a second. Let me see. Yeah, so there is indeed also material on QPy. So yeah, it's definitely also a framework to which can be quite interesting. So I'm definitely not promoting PyCUDA. On the contrary, I just showed it because it's a different approach, and also because I refer to it in the Numba section, and people might have been curious. But if you look at the QPy code, it should actually be very similar. There is most likely also the Mandelbrot example, etc. Mandelbrot example, etc., etc. No, I give a different example here. There I actually do a singular value decomposition directly on the GPU using a linear algebra function, which is defined by QPy. So QPy is quite nice as a framework for scientific computing, and it's quite valuable in that respect.
Yeah. And regarding NVIDIA Rapids, which is another
Yeah. So
approach.
Rapid is mostly for dealing with data frames. So I personally view it as the pandas on GPUs, essentially. So it can be useful, but if I look at the performance gains, there are a number of things. So basically, you will have a restriction due to the limited memory size of your GPU. So that is going to limit the size of your datasets. And yes, it's going to perform very fast on moderately sized datasets. And very fast, in some experiments I did, if memory serves, was a factor of 3 to 5. So the question is, are you going to gain enough with rapids in order to, let's say, offset the limited amount of RAM you have available? So it's a bit of a strange, rapids to me is a bit of a strange thing. I can imagine quite a number of use cases where it's really useful. So if you have intensive processing on a data frame that's not too large, it's going to be useful. If you do processing on many data frames, it's very useful because you can do them one by one. But if your problem is that you have huge data and that's why your processing is slow, rapids might not really help you that much because you're restricted to whatever memory you have on your GPU.
Yeah.
So that would be a bit of an answer to that question.
Yeah, it makes sense. I think each framework can be used for a different use case.
Absolutely.
And I think it's from our perspective to actually analyze that first step. But I think there's another question. I think it was regarding the GQPy example, actually, that you showed. And the question is, isn't SVD very bad at GPUs?
SVD is very bad everywhere. I mean, even on even parallelized, it's pretty awful. So yeah, it's likely not going to be. I can have a look at the numbers because I think I benchmarked it. So let me see. It was not terribly impressive, to be honest. But let me have a look. So basically, if I compare it with SciPy, let me see how large my data is here, because otherwise, of course, things don't make any sense. Okay, that's 1,000 by 1,000 matrix. So, okay, that is small, essentially. Let's see what SVD does on that. So SciPy would take half a second. QPy would take actually 10% more. And okay, so a QR decomposition would be 130 milliseconds for SciPy and 14 milliseconds for for the GPU. So indeed, the SVD is doing pretty badly.
Yeah.
But
Yeah.
okay, really not unexpected. I mean, try it with LAPAC, and you're also going to be extremely unhappy with the scaling. So yeah, it's not unexpected.
It makes sense. SVD is bad overall.
Yeah. Unfortunately, yeah. It's very useful, but well.
Exactly. It's difficult. Okay, I think there's not any more questions.
Okay.
And one last question actually that we are left with is the code will be publicly available, so we'll send you an email to actually
Yes.
have
I'll send you a link to the repository, which is
and we'll update then the web page. But so everyone knows, we'll update it and send even an email reminding that. And I will just, without further ado, try to finalize this webinar. And thank you once again. That was really interesting, and I was not familiar with Numba, and finally I am. So it's been actually really interesting for me. I will not compile things and try to put everything on CUDA on my side, but hopefully eventually I will do it. And once again, thank you so much. Just for closing, and December 2, we'll have another webinar. So this webinar will also be similar to this one regarding the time zone and time. And we'll actually delve into how to profile your Python code. And then we'll have the hackathon that actually will be in hybrid mode. So you can go to Stockholm and visit Stockholm, but you can actually attend this hackathon online. So hopefully you were able to attend it. And once again, thank you so much, everyone. And hopefully we'll see you on the 2nd of December once again. Thank you. Thank you, Geert, once again. And
My pleasure.
bye.